Hi, welcome to this study guide or unit test on solutions in chemistry. Before we get started, I want to make the point that this title up here for each slide is going to correspond to a video that is already on this channel. So if you find that you have difficulty with any of these questions, I would recommend going back through the channel and checking out that specific video to make sure that you feel really good about it. All right, let's get started. The first question here is to write the reaction for the following substances dissolving in water. We have K2S, NH3, and LiOH. So here we have it. The potassium sulfide is ionic and it is soluble because potassium is a group 1 ion. It'll always dissolve. That will break into two potassium ions, each with a +1 charge, and the sulfide ion will carry a -2 charge. If we want to be really specific, these would be labeled AQ for aqueous, but truthfully, most of the time ions are aqueous anyway. I'm keeping it very simple. Also, probably good etiquette would be to throw an H2O over the top of this arrow just to indicate that it is dissolving. Next, we have ammonia, NH3. Ammonia does not dissolve in water. It does dissolve, but it won't dissociate. So the NH3 is still going to be NH3, but at this point, again, you may want to put that little AQ to indicate that it is aqueous. Last up, the lithium hydroxide. It will always dissolve because lithium is a group 1 ion. Hydroxide typically does dissolve. There are a few ions that will prevent hydroxide from dissolving, so make sure that you know those rules if that's something that your teacher wants you to know. The lithium hydroxide will break into a lithium +1 ion and a hydroxide -1 ion. Up next are the factors that affect solubility. The question is, under what conditions would a solid calcium hydroxide dissolve best in water, and under what conditions would gaseous HCl dissolve best in water? The primary difference between these two compounds is that one is a solid and the other is a gas. At this point of the question, you probably should realize that both of them will dissolve in water. So because the calcium hydroxide is a solid, we are going to want a high temperature in order for that to dissolve well. We want to stir and crush the sample so it'll have a large surface area. Stirring will Okay, so the high temperature and the stirring together are going to move the water molecules around so that those calcium and hydroxide ions can kind of squeeze in between the water particles. And then we have the crushed sample. When the sample is crushed, more of the calcium hydroxide or the solid sample is going to come in contact with water, so it'll dissolve more quickly. And then lastly, we want our solution to be pretty dilute. When there's less stuff dissolved in the water, the calcium hydroxide will have an easier time finding little pockets between the water molecules for it to kind of like get cozy and dissolve. When the solution is very concentrated, whether it's concentrated with calcium hydroxide or something else, the solid will have a tougher time dissolving. Next up, we have the gas. So because this is a gas, we want our solution to be very, very cold. And this is because the gas particles, whatever they are, in this case hydrochloric acid, they will rise to the top and try to evaporate because they're less dense than the liquid that you're putting them into. So if the water is cold, then the molecules are moving much more slowly, so the hydrochloric acid has a harder time rising out of the solution and evaporating. So if the solution is cold, that's a good thing. Then we don't want to stir or agitate because, again, that will move the water molecules out of the way and allow the gas to rise out of the solution very easily. We also want to increase the pressure on the solution because that's going to kind of hold those gas bubbles down in the solution, and they have to have a very high vapor pressure in order to rise out of that solution. And then lastly, again, we want our solution to be dilute. When we're dissolving the first, second, and third particles, that's really easy. But when we're dissolving, the first millionth, the second billionth, the third trillionth, it gets harder and harder to, in terms of atoms, millions, billions, and trillions is really not that many. But the more stuff you have, the harder it is for particles to continue dissolving. Right, for this question, you probably want to pull out your saturation curves or solubility curves, whatever you call them. And in this case, we are looking at the curve for potassium nitrate. Most of those curves have formulas on them, so you'll have to take that potassium nitrate name and convert it to a formula. And the question asks, a solution of 35 grams of potassium nitrate in 100 grams of water. That's not even a statement. We have a solution containing 35 grams of potassium nitrate in 100 grams of water at 40 degrees Celsius. The question is, how much more solute needs to be added in order to saturate the solution? And then the second or follow-up question is, how much more solute would you need to have 200 grams of water and then that solution be saturated? All right, here we are looking at the solubility curve. Here, this graph tells us that we are in 100 grams of water. Oh, that is a very fine point. And we are looking at KNO3, that is potassium nitrate. We were at 40 degrees Celsius. And at 40 degrees Celsius, our solution would be saturated roughly at 65, perhaps, grams of solute. Let's just say for the sake of the math, it's 65 grams. I would anticipate that if your teacher gives you this question, either it's multiple choice and there's a very clear answer, or it's an answer that, because you're reading the graph, there's like a window of correct answers. Because some may say that that's 64, some may say it's 66. I mean, it's obviously not 60 and it's obviously not 70, but I would be sure that there is like a window of correct answers. So don't go crazy over it. So that is the maximum amount of KNO3 that will fit in this solution, but we currently have 35 grams of KNO3 in our solution under these conditions. So if we did the math, the 65 maximum minus the 35 that we have would give us 30 grams of solute that is still able to dissolve. If we're working in 200 grams of water, then theoretically we should be able to double the maximum amount of allowed solute in the solution. So instead of the potassium permanganate holding 65 grams of KNO3 at a saturated solution at a temperature of 40, because we've doubled the water, we can double the amount of solute that we can dissolve. So this 65 will turn into 130 maximum. We still have the 35 grams that are in there, so our solution now is like a lot less concentrated. And if we did the 130 minus the 35, that would tell us the new addition that we can add to the solution before it's saturated. So we would make this 12, and then this is 10. 10 minus 5 is 5. 12 minus 3 is 9. The answer there would be 95 grams. Up next are some solubility rules. So we have a list of a few compounds here, and you should either use your memory or your solubility charts to figure out if any of these compounds, are soluble. All right, here we have it. The sodium sulfide is soluble because sodium is a group 1 ion, and it's always soluble no matter what. Same goes for the potassium nitrate. Nitrates also really love to dissolve. Then we have magnesium chlorate. Chlorates love to dissolve. That is soluble. Then we have iron 3 hydroxide. Like I said earlier, hydroxide is one of those ions that typically doesn't like to dissolve. It kind of depends on who it's bonded to. The iron says, I'm not interested in dissolving, which really means that this is a decently strong bond. They don't want to break apart just because water's around. So in that case, the result is an insoluble compound. Up next is silver chloride. And silver chloride, the halides usually like to dissolve. So the members of group 17, usually they love dissolving, but there are 3 ions that prevent the halides from dissolving. That is silver, lead, and mercury. If any of the halides are bonded to one of those 3 ions, then they do not want to dissolve. So because silver is one of those 3 ions, silver says, chlorine, you're not going anywhere. You're stuck with me. So they will not dissolve if added to water. Calcium carbonate. Carbonate, again, is kind of like hydroxide, where it doesn't usually like to dissolve, and calcium agrees, we're not dissolving, so that is an insoluble compound. And the sulfates also. The sulfates, again, are not known for their dissolvability, and barium agrees, we're not dissolving, so that is an insoluble compound. If you are using the New York State reference tables, which personally I recommend, This is kind of how I have always instructed my students to read these tables. And that is, this is two separate tables here, but this inner circle, if a compound winds up falling in this circle, then I would consider it insoluble. So that iron hydroxide, or iron 3 hydroxide rather, that is a hydroxide ion, and hydroxides fall in the circle. The iron that it's bonded to does not take it out of the circle, so that is why the iron 3 hydroxide was insoluble. Looking at that sodium sulfide that we had, Na2S, the sulfide usually doesn't like to dissolve, but it got taken out of the circle because it was combined with a group 1 ion, the sodium. The carbonate didn't like to dissolve, calcium carbonate. It's actually seashells. The carbonate doesn't like to dissolve, and the calcium was not able to take it out of the circle because it's not a group 1 and it's not ammonium. So the calcium carbonate stayed in the circle. The silver chloride, chlorine usually likes to dissolve, but silver dragged it into the circle, so that made it insoluble. Sulfates. Sulfates usually like to dissolve, but they have quite a few exceptions. And I always see sulfate bonded to a group 2. So that's important to note. Those are all group 2s right there. So the sulfates, they like to dissolve, whatever. They're kind of iffy with all these exceptions. Calcium brought the sulfate in. Was it calcium? Calcium brought it into the circle? Or perhaps it was barium. I just double checked. It was barium. Barium brought it into the circle. So that made the barium sulfate insoluble. So if you're looking at these tables, this is how I recommend you read it. In the circle is insoluble. It's pretty nice to remember. It's important to note that these compounds in this blue box, nothing is going to take a sodium and get it to not dissolve. Sodium and all of the group 1 ions will always dissolve no matter what. And the same is true for all of these compounds here. All right, now we have lesson 9.5, which is my favorite of the entire year, precipitation reactions. And the question is, what are the products of the following precipitation reactions? So I'll let you go. It's important to remember that precipitation reactions are double replacement reactions. So what's going to happen here is that the sodium is going to pair up with the chlorine and the potassium is going to pair up with the nitrate. But because we're working with 2 group 1 ions, everything is going to dissolve and nothing is going to rebond because the potassium and the sodium love being ions, just swimming around water. Nothing is going to get them to bond to something else unless, of course, the water is evaporated out, in which case they would be left behind and they would find something to bond to because all the water's evaporating. So truthfully, we would have no reaction here because all of the resulting products are soluble. Now over here, we had to, of course, balance the equation. We had lithium phosphate and magnesium chlorate, and those had to swap partners for the double replacement. So lithium paired up with the chlorate and magnesium paired up with the phosphate. So I had to break them apart and re-crisscross them. So the 3 here belonged to the phosphate. The phosphate gave that 3 to the magnesium when they swapped partners. Looking at this, the result is that the lithium is a group 1 ion, so this would be soluble aqueous. The magnesium phosphate is not soluble, so it would form a solid product, which would sink to the bottom of the container. So I've labeled this PPT for precipitate. You may also want to label it S for solid. I don't like using solid just as the teacher, just because some students will associate solid and soluble. Don't do that. S is for solid. So I've just done PPT so we could have this little discussion right here. And then, of course, my equation is balanced. I have 6 lithiums on each side of the equation. I have 6 chlorates on each side. This 3 times that 2 gives us 6 of the chlorates, 3 magnesiums, and 2 phosphates. And that is your reaction. Now down here, I have calcium sulfide and ammonium chloride. Remember, ammonium loves to dissolve all the time. There's no exceptions on an ammonium, so that's certainly going to dissolve. But the calcium sulfide is insoluble. So once I add it to water, there is no breaking apart. It doesn't dissociate. So for that reason, the calcium and the sulfur ions don't have the ability to break apart and go swap with the ammonium chloride. So they are not going to react. So that's why there's no reaction in that final case. Up next are some concentration questions. First off is percent by mass. We have a solution that has 12 grams of solute in 225 grams of water. And then finally, we have what is the amount of solute dissolved if we have 250 grams of solution, and the percent by volume is 78%. When I set up these questions, I try to get it so that like you kind of get the little tricks as we go. So for this first question, the 225 grams of water, that is just the solvent. That's not the entire solution. That's why I had to add the 12 grams of solute to the 225 grams of water across the bottom here. And the 12 is just the solute. This is the solvent and the solute, making the solution. So when we divide and multiply by 100, we get 5.06% for that percent by mass. And then over here, we're working backwards. We're given the percent by mass and asked to find the amount dissolved, just the solute. I'm told that the solution is 250 grams, so that's going to go on the bottom. No need to add anything there. I am going to take this 100 out and convert my percent to 0.78. That is a mathematical equivalent. And then I will take that 0.78 and divide it by, or I'm sorry, multiply it by the 250 to get x. So it's kind of like a cross multiplication. You'd put the 0.78 over 1. And finally, I would get 195 grams. You also can plug this 195 back in for x to check your work just to make sure that everything went well and that you did it correctly. Next up is a parts per million question. And here we have it. What is the concentration of a 0.25 milligram of lead in 10 liters of water in parts per million? Knowing that the density of water is 1 gram per milliliter. I think it's also important to note that you can do a parts per billion. It's just at the end of the equation, instead of multiplying by a million, you'd multiply by a billion. A few things had to happen here. I had to take the 25 milligrams and convert it over to grams. And then I had to take my 10 liters of water, convert that to milliliters, and then using the density formula, figure out the number of grams that this is. So this blue and green wound up in my parts per million final problem. And when I divide and then multiply by a million, I got 0.025 parts per million. How do you prepare a 500 milliliter solution that is a 0.75 molar solution of potassium permanganate? That's a loaded question. There's a lot that comes with this. So the first thing I did was I found the molar mass of potassium permanganate using my classic QMT charts. I love them. They're so organized. So the molar mass of potassium permanganate is 158.04 grams per mole. And I took my molarity equation, plugged in what I knew, and here I know I'm looking for the number of moles of potassium permanganate, which came out to 0.375 moles of potassium permanganate. So that's a number of moles, not a number of grams. So I can't use it in a lab setting, but I can use it for like concentration and anything involving like a chemical reaction. I can use that number there. But in a lab, I have to use grams. So I have to take that number of moles and convert it to grams, and I did that using my molar mass from the QMT chart. don't know how many grams it is when I have 0.375 moles of KMnO4, but I do know that it's 158.04 grams if I have 1 mole. So I crisscrossed and solved for X, which came out to 59.265 grams of KMnO4. So what you do, you take the solid and you put that into the volumetric flask. Using a funnel, you get every tiny little grain in there. A lot of the time we keep the funnel on there and we'll rinse the funnel with the water that we're adding to the flask, and you have to fill to the line, and that is it. And it will have to go in a 500 milliliter graduated cylinder. I'm sorry, a 500 milliliter volumetric flask. You can't use a graduated cylinder because the solid is going to take up some space. So if you measure 500 milliliters in a graduated cylinder and add it, you would actually overfill the volumetric flask a tiny bit. We want the solution to be 500 milliliters, not the solvent. So that is why you have to add the solid to the volumetric flask first. Everyone's favorite, colligative properties. What three things happen to the physical properties of water upon addition of any salt? I guess it's also true if you add something covalent. That's okay. So long as it dissolves. How do these things differ if the salt is calcium chloride versus sodium chloride? Anytime you dissolve anything in water, whether that is a salt or it's sugar or something else covalent, the boiling point is going to increase. It is harder to boil your sample. The freezing point is going to drop. You need to remove more energy to freeze your sample. And the vapor pressure, additionally, will decrease. Your solution has a harder time just evaporating on its own. Next up, the calcium chloride is going to break into 3 ions. It'll have 1 calcium and 2 chloride ions. And then the sodium chloride will break into 2. It'll break into 1 sodium and 1 chloride ion. So the calcium chloride has a third particle that is interfering with water boiling, freezing, and evaporating. So any change that is seen in the calcium chloride and the sodium chloride, assuming you have equal amounts of each, like moles wise, the calcium chloride will have a more dramatic effect on the boiling point and the freezing point and the vapor pressure. So you'll have to add even more energy to boil, remove more energy to freeze, and it's going to require more energy to evaporate. So more ions equals more dramatic change. Last but certainly not least is solution stoichiometry. We have a question: what mass of solid silver bromide is produced when 100 milliliters of 0.150 molar AgNO3 is added to NaBr in excess? I just want to point out before you get started, this NaBr in excess means that there is no limit to the amount of sodium bromide that you are reacting. The limiting reactant, I learned it as limiting reagent. So I always want to say limiting reagent, but regardless, it means that this 100 milliliters of 0.150 molar AgNO3, that's what's controlling the situation here. There are some chemistry classes that will teach, you have 2 amounts of stuff and you have to figure out which one is controlling the reaction. In this case, I've told you that NaBr is in excess, so assume there's an infinite amount of it, meaning that the AgNO3 here is the one controlling the reaction, and you only have to focus on these 2 numbers. First step of any stoichiometry problem is to determine your chemical reaction and balance it. So this, of course, is a precipitation reaction. We're getting solid AgBr. That's how we know. I started with AgNO3 and I'm reacting it with NaBr. That's a double replacement. I just swapped them. Luckily for us, everything has a charge of either +1 or -1, so not a lot of crisscrossing and no need to balance. It's already balanced. So what I've done is I've tried to determine the number of moles of AgNO3 based on the data given from this solution. So I've plugged in my 0.15 molar and my 100 milliliters, of course, got converted to liters. Solved for the number of moles, and I got 0.015 moles of the silver nitrate. Looking at my chemical reaction, at this point I would do a mole ratio, but because my reaction is a 1-to-1, I don't actually have to do any math. I know that I am working with 0.015 moles of sodium bromide. I'll have to take that number of moles and convert it to grams. I didn't do a QMT chart because it's just adding these 2 numbers together, but it comes to 102.89 grams per mole. I know that 1 mole of sodium bromide is equal to 102.89 grams, but the question is, how many grams is it when I'm only working with 0.015 moles? Crisscross multiply, solve for X, and I am left with 1.54 grams of sodium bromide. That's everything on solutions. Of course, feel free to rewatch the video. Go back to any of these videos listed across the top to make sure that you feel really confident before going into your unit test. If there's any questions, of course, please leave them in the comment section below the video. Subscribe so you don't miss our next lesson. We are going to get into kinetics. I don't love kinetics, but I try to make it fun. I hope to see you there. Bye.